Hello, everybody. My name is Nicolas Rinaudo. I'm currently employed at JP Morgan, where I work on code generation, which is basically taking specifications written by domain experts and turning them into code for different target languages. You can think of it as ChatGPT or Copilot, except without all the obvious bugs, security issues, or the grand theft autocomplete aspect. I'm here. Well, the real reason I'm here today is because a friend of mine asked me yesterday at lunch. They really needed somebody to be on that stage, anybody to be here for you today. Turns out I am anybody, lucky you. So I am going to stand here for the next 45 minutes. I prepared this talk yesterday for lunch. So this is the best effort. I have no idea how long it's going to run. It might be 45 minutes, it might be 2 hours. I don't know. We'll find out together. But now that I'm here, I want to teach you how to write a programming language from scratch. And you might be wondering, why would you want to learn that? And there's a couple of reasons. The first one is you use programming languages presumably as part of your day-to-day work all the time. And so writing your own tool is going to give you insights. It's going to update your mental model about how these things work. And it should, in theory, make you a better programmer for it, which is nice. The other reason is if you can do the hard thing of writing a general purpose programming language from scratch, which is what I'm going to teach you, then it should be a lot easier to do the relatively simpler task of writing a domain-specific language, which, if you find yourself maintaining software that whose domain experts are non-technical, can absolutely change your life and is going to allow you to outsource most of your work to the people who actually know how to do it and focus on what's fun, which is fixing bugs. So it's very important to learn how to do that. It's going to make, in theory, your life a lot easier and more fun in the future. The reason I feel I'm qualified to talk about that is I've gone through that exercise twice already as part of my work. I had to implement 2 different programming languages, and I felt it was really fun. So after I'd done it twice, I decided I probably should study how that's actually done because I have no clue what I'm doing. And I went to study it and discovered that I had fell into absolutely every possible trap I could have, plus a couple nobody knew about. I'm quite talented that way. And so I can show you, I have some practice, I have some theory about this, and also I know all the failures. I've done them all. So I feel that I'm qualified to try and explain to you how we invent a programming language. So before we continue, what is a programming language? What is a program? Which is what you manipulate and create every day, isn't it? Well, you should think of it as source code, right? It's just text, and then you do something with it. And the various things you can do with it are really taking that text, taking that program, and turning it into something else. You could, for example, take that program and shift things around so that it looks nicer. So that would be, we call that a code formatter. And if you're not using that as part of your CI, you definitely should be. We could use that to interpret the code and simulate the running of the code and give you the result. We'd call that an interpreter. You could use that to turn your code into code in a different language. We call that a compiler. So you could go, for example, from, I don't know, whatever we're going to work with to Java, and eventually, ultimately, you'd turn that into machine language, which is another language that the machine is going to interpret. So these are the various things we could be doing with source code. And what we're going to focus on in this talk is mostly the interpretation. And if we have the time, which is not at all a given, we might do some type checking as well, because that's quite fun. So we're going to be talking about interpretation. What we are not going to be doing at all is worry about the syntax of a language. We're not going to write a parser. We're not going to define a grammar. Those things are extremely fun and important. Not my points, and they deserve a different talk. So we're going to assume we already have a function from our grammar or language to whatever it is we're going to use to represent our code. Mostly because if I wanted to talk about that, it would be a 4-hour lecture, not a 45-minute one. So let's focus on what I actually want to talk about. And before we start doing that, I want to give you some intuition about how these things work. And this is going to be through the substitution model, which is not necessarily something you're already familiar with, but it's quite simple, really. So this is a kind of program that we're going to be manipulating, which is fairly straightforward, but we define a function and then we apply it. And I like to think of programs as 2 different sets of things. You first have these kind of instructions which give you knowledge. This is defining the function f as a function that map x to x plus 1. It's knowledge that you have, it's not code that you run. So I'm going to move that to the knowledge area of my screen. And that is a target. This is what we want to, this is the code that we run, which is function application. And we'll do that by noticing that f, we know the definition of f. So we can replace f, the application of f, with the body of f and the knowledge that x is equal to 2. And once we've done that, we can keep reducing. X is known to be equal to 2, so we're going to replace x with 2. And then we're going to replace 2 plus 1 by 3, because we can reduce that. So that's your basic intuition. But we want to go a little bit further than that, because there are some ambiguities with what I just described. Take this, for example. You don't need to worry too much about the code. It's just to show you stuff. So we have information about f, which we move to the knowledge part. We have information about j, which we move to the knowledge part. And then we do the same thing of substitution. We know the definition of j, so we're going to replace j with the body of j and keep knowledge about y. And at this point, we have a choice. We could either substitute f for its definition, or we could substitute y for its definition. And we don't know which one to do. And that's actually a pretty important choice to make. So we're going to study both really quickly, because it's not that important. It's just we need to make a call. And they're kind of equivalent. You would hope that whichever way you go, you get the same result at the end. And yes, you should, in the same language. So you're not programming in Go, for example. In the same language, you would get the same result. But they do have different, for example, they don't perform as well. One can be faster than the other, depending on the time. So to show you that, I'm first going to do innermost substitution, which is this, where I find the parameters of a function, the arguments of the function, and then I reduce them as much as I can, and then I'm going to reduce the function. So that's going to be called innermost substitution. So here we would replace y by its definition. Notice a counter at the bottom. I'm counting the operations that I'm doing. Then reduce this to 5, replace f with its definition, replace x with its definition, and then do the addition, and we get the result that we expected, 10 in 6 steps. If we were to do outermost substitution, so replace f by its definition before replacing its arguments, then we'd get first x plus x. We know the definition of x, so we'll substitute it for its value. We know the definition of y, so we'll substitute that for its value. And then we just keep reducing until we get to the normal form, which is 10 again, which is the value that we wanted to have, right? So we have the same result, but 7 steps. So this was actually more expensive to compute than innermost substitution. And you'd think, well, that's great. We know which one is faster, so we're just going to do that one. Unfortunately, depending on the scenario, the other one, outermost, might be faster. We don't have enough information about programming language for me to show you that, because we don't know about conditionals yet. We will soon. We don't know yet, so I can't show you. But there is no obvious better approach. We're going to do innermost substitution, because that's what most languages do. The only language who doesn't do that I know of is Haskell. But most of you are probably more used to innermost substitution, which is known as eager evaluation. So whenever you can reduce something, you reduce that. Outermost is known as lazy evaluation, so you only evaluate something when you really have to. So you evaluate the arguments when you don't have a choice, right? If you went to the talk this morning, it's call by name, call by value, same thing. All these things represent the same notions. Right, so what we learned so far? We've learned that interpretation is done by substitution. You have your code in specific chunks of it for the knowledge that you have until you cannot reduce any further, and that's going to be the result of your program. We've learned that innermost substitution evaluation is called eager, and outermost evaluation is called lazy. And we are doing innermost. Right, so that should have built the basic intuition you need in order to think about a program and how to work with it. But in order to do that, we have seen it's a function from your program to the result interpretation, isn't it? So we need some form of representation of the program in order to apply a function to it. So we are going to work on that now by defining the simplest possible programming language. Only supports numbers. There's a number. That's all we can do. That's not super interesting, but we know that we somehow, in our programming language, must be able to represent the notion of a number. Let's make it slightly more interesting with a very simple function, addition. Right? So we know now that we need to be able to represent two things, numbers and the addition of two numbers. So an expression of a language, a term of a language, can either be a number or an addition. whenever you're working with something that is one thing or another, you should think some types. It's always going to be the answer. So we're going to create, I'm using Scala as an exposition language. So if you don't know Scala, none of the code is going to make any sense, but that's fine because I'm highlighting the part that are important. You don't need to understand the Scala syntax because nobody really does. Right, so you have a sum type which is called expression, X for expression, which is either a number, so 1 or 2, or addition, which has two members, the left-hand side operator and the right-hand side operator. Easy enough, right? And now we are going to want to work on the interpretation of that. And in order to do that, because I can and because it's fun, I'm going to give you some formal syntax in order to define the operational semantics of our language. So that's a lot of very fancy vocabulary because I like to sound smart, but it basically means we're going to define a syntax that allows us to formally explain how each construct of a language works. If that's still confusing, let me unconfuse it. Number. This reads as number that wraps a value, interprets or is evaluated to whatever is on the right-hand side. I'm going to be using these triple question marks a lot. That means there's going to be something in there. We don't know what it is yet. And, well, what does a number evaluate to? Do you think? What does num of value evaluate to? Anybody has any idea? It's going to evaluate to the value that it wraps, right? So we know evaluation returns an integer. Addition now. Addition is composed of a left-hand side and a right-hand side. And we want it to evaluate to something. We want to say, logically, well, that's going to be the addition of the left-hand side and the right-hand side, right? But that's clearly incorrect. Do you see why? Left-hand side and right-hand side are expressions, they are terms of a language. We don't support addition yet because we're implementing it. So we need somehow to turn them into integers. So we need to evaluate them. So we need to be able to say something like, well, sorry, these are not the right type. We need to say, if left-hand side evaluates to some value called v1, and right-hand side evaluates to some value called v2, then, and that long vertical bar separates our preconditions from our conclusions. So whatever goes above the vertical bar is going to be called an antecedent. These are all the things that we must have. And if we have all these things, then whatever is below the bar, called the consequence, are the conclusions that we can draw. So here, if left-hand side evaluates to v1, etc., then we can conclude that the addition evaluates to v1 plus v2. These are the formal semantics that we are going to be using throughout the rest of the conversation. Yeah, that works, conversation. So now let's write an interpreter for that. We take an expression. Expression is a sum type. The only way we know of working with sum type is pattern matching. So what we have, first we're going to do num, right? These are the semantics at the bottom. So which I'm going to fix because we always need to have antecedent and consequence. Number is a special kind of expression because it doesn't have any antecedent, which means it's an axiom. It's always true. Whenever we meet num, then it evaluates to that, whatever the state of the rest of the word. Right, so we have the case num, which is composed by a value, and we know that when we find that, we are going to return the value. Simple enough, right? There's a very clear mapping from the formal semantics to the actual code. So if you can't read Scala, you should probably at least be able to read the formal semantics. Add now. Add has two members, left-hand side and right-hand side, and we said that the result was, well, I'm going to outsource that to a different function because otherwise that screen is going to get too messy and we will not have enough room on the screen. So let's do add. And this says that we want to evaluate LHS to v1, RHS to v2, and then return the sum of the two. Pretty clear, pretty simple, pretty easy. Let's make sure it works. I'm going to write an expression that represents 1 plus 2, add of 1 and 2. Yes, you can clearly see that our expressions are going to be extremely verbose. So very soon I'm going to stop writing them all because they take 7 screens in order to display whenever we start working with functions. And then when we evaluate that, we get the result that we were hoping for, 3. Right, 1 plus 2, 3. We have made magic. This is amazing. And this way of representing expressions is extremely useful. It's so useful that it has a name. This is called an abstract syntax tree, which we also call AST for short. Abstract syntax tree is composed of two things, abstract syntax and syntax tree. So abstract syntax, because, well, that, if I had the parenthesis, that's going to be the exact same expression, isn't it? The parentheses are noise for the human reader to allow us to do the good stuff, but we don't care about them, so we're going to abstract over them. Similarly, that's exactly the same expression. I mean, the text is not the same, but the result is the exact same expression. So we abstract over the details of our expressions and store them as an abstract syntax tree. The tree bit now. Well, this is really a tree, right? We have the operator as the root of the tree, and we have the operands at the leaves of the tree. That's not much of a tree, though, is it? It's got a maximum depth of 1, cannot grow. It's very constrained. It's much more of a bonsai than it is a tree. But we're going to fix that. Because what if we wanted to have nested expressions? What if we wanted to do something crazy, like do 1 plus 2 plus 3? We don't have the tools to do that. We can't do that because we only have add, which takes numbers, and numbers. The fix should be fairly obvious. We should say that this was actually a bad design decision. Addition is not the addition of 2 numbers, it's the addition of 2 expressions, right? And then our tree becomes complete and can have arbitrary depths and we can have arbitrary nested expressions, which is lovely. Yes, we have to fix add because it's taking numbers and not expressions. But we don't have to fix anything. Interpret takes a number, takes an expression. So both of these things still work, and we still get the result. This would have been a hint, by the way, that we wrote add incorrectly. Interpret takes an expression, so we should not have constrained the members to be numbers. Right, what's next? Oh yeah, we're going to make sure that this all works. So we're just going to do nested expressions and check that it does in fact evaluate to 6, what we wanted. So far, so good. We've seen that our source code is represented as a recursive sum type. We've seen that it's called an AST, and we know that interpretation is done through pattern matching. Okay, so far so good? Right. Next, because we have a very poor programming language at this point. We know how to add numbers. We have made a weak calculator. Let's do something that's a little more like programming. Let's give our language the opportunity, a way of expressing condition, of taking decisions, which is typically going to be done something like that in programming languages that you know, right? If then else statement, where you have a predicate, and if that evaluates to true, then we are going to return whatever the then branch evaluates to, otherwise the else branch, right? So let's run that through our substitution model. Remember, eager? So we evaluate the operands before we apply the function. So we get obviously 3 here, 7 here, and this is true, so we return 3. Can anybody spot the mistake? It's not in the result is correct, obviously. Yes, exactly. I should only have evaluated one of the two. I did say when I described the conditional statement that if the predicate is true, then we evaluate the then branch, and if it's false, we evaluate the else branch. And here we evaluated both, which is a problem. So clearly our basic substitution model works, but we're going to need to tweak it for conditionals. This is how it's going to work. What we want to say is that if the predicate is true, then we evaluate the then branch, and then we replace the entire conditional by the result of evaluating the then branch. That's a good intuition to have, but we need to formalize it now. Right, conditionals, we have a predicate, an on T for on true, on F for on false. And the way it's going to work is the first thing we're going to do, we're going to evaluate the predicate. And there's 2 possibilities here, isn't there? We can either have a predicate that evaluates to true or to false. And we don't really have syntax to represent that choice. I haven't introduced it anyway. Well, the way we're going to do it is to write 2 different rules, right? One when the predicate evaluates to true, and one when it evaluates to false. And then it's very easy. It's exactly what you'd expect. We'd say that in the case of the predicate evaluating to true, then we evaluate on T to some value V and we return V. In a case where it evaluates to false, then we evaluate on false to some value V and return V. So the semantics of if then else statements or conditionals are pretty straightforward when you think about them. But there's a trick, right? Because we don't want to be evaluating both branches. So now we are going to need to update our AST in order to support conditionals. Fairly easy. We know we have con, so we're going to add a new variance to our sum type, which has a predicate, an on-true, and an on-false branches. Now that the AST is updated, we are going to update the interpreter by adding condition with all the members. And again, I'm going to do that in separate function for reasons of screen real estate. Cond. Well, the rules tell us if it evaluates to true, then we evaluate the on t. Otherwise, we evaluate the on false. That's not right, is it? What's the return type of interpret? Returns an integer, doesn't it? That, at least in Scala and other sane languages, you cannot compare an integer to a Boolean. That doesn't exist. So we could do that. We could be insane. We could say, right, well, let's do that. Let's pretend that all integers can be mapped to Booleans. This is not how my mother raised me, so we're not going to do that because this is just evil. It's called truthiness, and we're not doing that. We're doing proper types. So in that case, we have a problem because we need to be able now to represent the fact that our interpreter might return either an integer or a Boolean. And at the moment we can't. We're just saying it returns an integer. So we need to have some type that represents the possibility of being an integer or being a Boolean. Again, just to show that it's an int. Again, some type, right? We have either a number or a Boolean. So we're going to have number or Boolean, and thus those are all of our possible values, which will make us update interpret to return a value. And now we're going to have to fix a few things. Number value doesn't evaluate to a value any longer. It's going to evaluate to a value.num, right? Now we have typed return values, which is interesting. Similar. Right, and now we're going to do add. As you can tell, I didn't finish this deck until it was 40 minutes ago, so there's going to be some transitions which I'm not super familiar with it. Addition, we are saying that v1, well, we want it to be a number, right? When we add two numbers, it cannot be any value, it's got to be a number. So we're saying left-hand side and right-hand side must both evaluate to some values that are numbers. And if that's the case, then the return value is a number that contains the sum of the two numbers. Again, fairly straightforward. I'm not sure why I highlighted that. I'm sure I had a good reason, but I can't remember it right now. Right, yes, is to say we want to make sure that those are numbers. Our implementation of add doesn't do any of these checks. So let's just throw that away and start it from scratch. Where we're saying we interpret the left-hand side, and we want to make sure that it's a value.num of v1. Same for the right-hand side, and if we have these things, then we can return the right value. And of course, we must handle a scenario where at least one of the operands is not an integer. So for all the other scenarios, we're just going to fail with the type error. So yes, we are definitely doing a dynamic language where types are checked at runtime. I hope I have the time to show you how to not do that, because I'm not a big fan of that either. I have opinions, you might have noticed. Right, and now condition. Let's implement condition. Well, we want the predicate to evaluate to a Boolean. If it evaluates to the numbers, then that's not correct. We are going to rewrite the entire thing so that if the predicate evaluates to true, then we know we're going to return the result of evaluating on t. If it evaluates to false, then it's going to be on false. And otherwise, we have another type error because we can't work with a predicate that it doesn't evaluate to true, to a Boolean. I was afraid of that. So, not my clicker. Monica, kindly lend that to me, but there's a trick button that turns off the screen for some reason. I think it's just to trick speakers. Right, where were we? There. Right, so now we want to evaluate to make sure that our implementation works. We can't really do that though, can we? Because do we have a way of expressing true in the language? We have a predicate, right, which evaluates to true, but we can't write the predicate because we don't have a way. We have a value type Boolean, but we don't have a statement, a constructor of a language that allows us to create one. So we're going to have to do that. We're going to have to create bool, which wraps a value and then returns a value.bool. Right, fairly easy. Update exp accordingly, bool that wraps a value, and updates interpret accordingly, proof of value, which evaluates to a value.bool. Right, very straightforward. Now that we have that, we can write this expression, which is going to be cond where the predicate is bool true, the on t is 1, and the on false is 2. And if you run that, we're going to get 1, exactly as we were hoping for. So now we have additions, numbers, booleans, and conditionals, which is a lot more than we had before. What we've learned so far is conditionals have specific substitution rule. We could not apply the same substitution model, general substitution model that we had. We had to make special rules for it. Then they require supporting Boolean into a language. And do not let people who write programming language do truthiness. Please, it's not a good thing. We have conditionals. Next thing we expect from a language is going to be a way of naming things, which is traditionally called variables. I'm not going to call that variable because variable has a very specific subtext implication of mutability. And I'm not saying that mutability is bad, but I don't want to take that decision right now. We might have to have mutability at some point, but until we need to, I do not want to make the choice. So I'm going to call that let, because some very good languages have come up with that syntax and I love it. Right. It should be clear to everybody, right? What does this evaluate to? Yes, to 1, because we bind the name x to the value 1, and then we say, well, what is the value bound to x? It's going to be 1. That one should make you a little bit more uncomfortable, though. It depends on the language, unfortunately. It shouldn't compile. It doesn't make sense. It feels like it doesn't make sense, but some languages think it does. But the point I want to make is not that the language who do that are bad languages. The point I want to make is this should make it clear that there's a notion of scope for local binding, right? X bound to 1 is only valid in a specific subset of your code, and you need to define that. So I'm going to make that part of the syntax, like most ML languages do. We have a predicate here. That's not a predicate, that's a binding, in which we bind x to 1. So that's going to, we're doing a substitution model again. So that's going to move the notion that x is equal to 1 to our knowledge area. And that's a body. This is the scope in which that binding is going to be valid. It's very clear in the syntax where x exists. And then, well, we know the definition of x, it's 1, so we can just replace it and reduce little by little to 3. So that seems all right. But there are some edge cases. Take this one, for example, where it should be pretty clear what that evaluates to, right? X is bound to 1, so this is really 1. Then x is bound to 2, so this is really 2. We're doing 1 plus 2, that should be 3. Pretty clear, right? Now, how about we flip the operands? Well, that's an addition, right? The addition should clearly, it's commutative, isn't it? A plus b is always equal to b plus a, so that shouldn't change anything. But it's unclear, right? Let's run it through the model, the intuition that we had built. We're binding x to 1, so we'll move that to the knowledge area, and that's valid in that headed bit of code. And here we're binding x to 2. How do we do that? Well, naively, at least the way I did it, which didn't work at all, was to say, well, that's easy. X is now equal to 2, right? Fine. And then if x is now equal to 2, then this is 2, and then that's 2, and then that's 2, and then we evaluate to 4, and that's not at all the right result. Now, you might think this is obviously wrong, this is obviously unhealthy. Nobody in their right mind would write something like that. I give you Python. This is called dynamic scoping. Lots of languages have thought it was a great idea because it was slightly simpler to implement. It's a nightmare to work with. Python had that in the first versions. They changed that, but it took them years of hard work to get rid of that. It's a bad language decision. We don't want to do that. What we want to do is something called lexical scoping, in which you can look at a bit of code and know with absolute certainty, without knowing any of the rest of the code, what a variable is bound to. You can do that statically, whereas with this, we have to run the code to see what a variable is bound to, which is why it's called dynamic scoping. What we wanted to do, instead of replacing the value of x, this is words you might have heard, especially if you've been doing Rust recently, create a new stack frame and push it on top of the list. We have a stack, right? And whenever we're going to look for a value of type x, we're going to go through the stack from the bottom or the top, depending which way you're looking at. Anyway, the latest, all the way to the first one you encounter. So here, x, we're going to look for the first occurrences of x from the bottom. So that's 2. And then that evaluates to 2. And notice how when you finish evaluating that let binding, we pop the stack frame that was associated with it. Right? Once a variable goes out of scope, it disappears from the stack, which then allows x to be 1, and then we get 3. Oh, god damn it. Sorry. That's going to happen a few times. Just please laugh. And we get 3, as we were hoping for. Where did I go? Yeah, right. Okay, so now that we have an intuition for how let bindings work, let's do the formal semantics. let has a name, which is bound to a value, and then we have a body. And the way it's going to work, well, we're first going to evaluate the value, right? So the value is going to evaluate to some v1. But then we're going to want to evaluate body, and this is where we have a problem, because we said body needed to be evaluated in some form of environment where x was bound to 1, and we don't have a notion of environment yet. This is what we're going to have to do. That reads, in environment E, value evaluates to v1. Now that we have a notion of environment, we can go further, right? Because now we know that body is going to be evaluated to v2 in some environment. And what environment would that be? Well, it's going to be the environment that we had, and then we're going to push a new stack frame where x is bound to 1. So I'm going to write this bind name to v1 in E, right? And then once we have that, when we know that the entire thing is going to value to v2. So, and of course, we're going to need a way to, when we see x, go and look at it in the environment. So I'm going to call that var. It's just composed with a name, and the action of doing that is just going to be lookup in E of name, which is another function we're going to have to define. Good. Okay, we have all these things, and we're going to want to implement them in expressions. So we need, in our AST, so we're going to need let to have a name, a value, and a body, and var, which just has a name. And of course, the two names must match, right? So if you define x, you can only apply var x if you have defined x earlier. Now, before we go any further, before we start writing the interpreter for all that, we are going to have some form of environment. So let's write that. Some class that contains a list of bindings, which we don't have a type for, so let's make one. I'm going to call it binding, which binds a name to a value. That's exactly the word they've been using so far, so it shouldn't come as a big shock. And we needed two functions, lookup, which given a name finds the right value. So that's going to be pretty trivial. Finds the binding with the corresponding name, extract the value, or fails if it doesn't exist. And then bind, which creates a new binding, which binds name to the value, pushes that at the head of the stack, on top of the stack, and wrap the entire thing in an app. And I'm also going to do that because it's always polite to provide ways of constructing empty values for such classes. Great, so we have an environment now. We can work with interpret. We can update it. So first, we're going to fix all of our existing rules to take the environment, because we almost always need to declare the environment. So num has an environment, but it just ignores it. So does bool. It doesn't care about the environments. There are terminals of a language that already know the values. In the case of add, well, add also needs some environment, so we're going to pass it to the add function. And then here, left-hand side in the environment, right-hand side in the environment, and we're done. Same for con, we're going to need the environment and pass it everywhere. Right, and now we can write the implementation of let, which has a name, a value, and a body, and I'm going to apply the let function to it, but must not forget to pass the environment. It's extremely important, because otherwise we would not know where to bind it. And this is how let works. We will interpret the value to some v1. And then we're going to interpret the body to some v2 in an environment that is a modification of the previous one. So we're just going to call bind with the right parameters. Then once we've done that, then the result is v2. And that's all you need to define a let binding. And then variable application or variable elimination, well, that's fairly easy, right? We have the name, we have the environment, and we said it's just look up the name in the environment. So that's what we're going to do. Fairly straightforward. Let's see whether that works. I am not going to write that, because that takes 25 lines or something like that. So just trust me that the ... is actually the right expressions. And when we run that, we get 3 exactly as we should. And if you remember, I'm using the code that, if we had not implemented static scoping properly, would have yielded 4. So that's a proof that we've done it correctly. What we've seen, local bindings have a scope, and that scope can be analyzed statically, if you're doing static scoping, as you should. They can be shadowed, which is what we've done. I'm definitely not going to finish that talk, but at least you'll have learned something, I hope. The shadowing I should probably have introduced when I mentioned it is when you define x multiple times. So the latter x shadows the previous x for the time in the scope in which it's defined. and their interpretation requires an environment which we had to define and work with. Right. Okay, so let bindings, we do stuff, I'm going to be talking about using code. In let bindings, we do stuff like say, for any x, I can compute x plus 2, but x can only be 1, which is a bit boring, isn't it? It's a bit of a disappointment. You write chunks of code that are powerful and take parameters, but completely ignores the fact that you can take a parameter and hard code the parameter. What we could do instead is say something like that. This is a function that for any x returns x plus 2. And we could reuse that function, but then apply it to 1 to have the same result. And the intuition, the substitution model here is very straightforward. We replace a function application by the body of the function, and we move the value of the parameter to the environment. So we get x plus 2 where x is equal to 1, which obviously evaluates to 3. And you might think, well, that's nice and all, but functions without a name, if you can just apply them immediately, that's not super useful. We have just spent 10 minutes figuring out how to name things, how to use local bindings. So you could do something like that. That function is bound to the name f. And then we apply f to 1, right? Sorry. And it seems easy. Has one very important consequence. So, local bindings. We bind a name to a value. We have a value here, which is a function. In our language, functions are going to have to be values, which is also a pretty important decision to make. We are literally doing a functional programming language, because functional programming language is a language in which functions are first party. And I could keep going, but Juan is looking very uncomfortable, and I have another 5 minutes to take questions. So either we don't do questions, and I keep going until Juan kills me, and we do questions outside over drinks or something, or I stop now and take questions. Lots of very emphatic nodding. I don't know for which one, but I'm going to assume me keep talking because that's what I want to do, so we're going to do that. Let's try to finish functions, because those are interesting. We're just not going to do recursion. It's a shame, but... right, so we need functions to be values of our language. And a function is defined by the name of its parameter, a string, and by its body, right? That seems all right. That seems reasonable. However, let's run through that. So this seems reasonable, right? Y is bound to 1, so this is really the function that maps x to x plus 1. So surely this would evaluate to 3, would it not? Well, let's try that. We bind y to 1, so that's updating the knowledge. Yes. And then we bind, I'm sorry about all the swearing in the mic. I just realized that I'm doing it under, but he's probably picked up by the mic. I hope it's not on the video. We move the definition of f to the knowledge, definition of y to the knowledge, and then we apply f. Well, then we have a problem, because f is going to be x plus y with the knowledge that x is 3, y is 2, that adds to 5, and then we just pop every stack in the frame and we get 5. And if you remember, we wanted to get 4. We have a problem. We have a bug here. And it's a very important one, and I'm going to allow me to use a new word that you certainly have heard and potentially never understood why it was called that way. See, the mistake we made here is y is bound to 1 when f is defined, but it's bound to 2 when... Ignore everything that's on top. It's not meant to be here, and you were not supposed to see that this was slide number 422, which is an absolutely sane number of slides to have, isn't it? The entire talk is 875, I think, so we're clearly not going to do the whole thing. Anyway, so the problem that we've had there is that y was bound to 1 when f was defined, but it was bound to 2 when it was applied. And clearly, what we want then, in order to avoid the bug we just found, is for a function to be applied in the environment in which it was defined and not in the environment in which it's being applied. We need to store the environment in which a function was defined with a function, like that. And some people say that could be seen as a function closes over its environment. I don't know why the word closes, but this is why it's called a closure, because you bring the environment in which a function was defined with the function. And once you have that, well then the formal rules become very easy. Fun, for function, not for fun, takes a parameter, a body, and is going to yield a value, which has a parameter, a body, and the environment, because it's a closure, right? Apply takes a function, whatever we're going to apply to, and the argument of the function. And yes, I've been made sure that whenever I talk about function declaration, I talk about the parameter, and whenever I talk about function application, I talk about arguments, because those are the right terms. You can't switch them. And then, well, fun. It must evaluate to a function, right? Because we're applying a function. So this must evaluate to some function. The argument evaluates to some value v1, and then we must evaluate the body in some environment. This environment is going to be E prime, the environment that was captured, closed over by the function, but not just, right? It's got to be E prime in which we have bound param to value. So we get that. And once we have all that, then we know that apply evaluates to whatever the body evaluates in that environment. Implementation is going to be fairly easy. We have functions, before we do interpretation, we have to do the AST. So function which has a parameter and a body, and apply which has a function which can be an expression. This is important. You could hardcode that to a function, but then that means you would not be able to use a variable, because a variable is not a function. A variable might be bound to a function, but it's not a function. And an argument, which is an expression as well. And interpretation, function is easy because we just wrap everything and put it into the environment. So param body, and we just create a function, param body, and close over the environment at the time of declaration, not at the time of application. This is crucial. Another trap I obviously fell into when I implemented it. And that's actually in production right now. I need to fix it. And application has a function and an argument, and the implementation is going to be in apply, where we must make sure that our fun evaluates to some function. If that's the case, then we can evaluate the argument in a regular environment, in E, not E prime, and map that to V1. Then we interpret the body in the environment that has been updated. So not any environment, in E prime that has been updated with the right binding. And then the result is V2. And once we've done all that, well, of course, if it's not a function, it's a type error, obviously. And once we've done all that, then we can run through our problematic code from before. I'm not going to type that all. And it evaluates to 4, which is what we wanted. We were getting 5, but now we're getting 4 exactly as we should. So what we've learned so far is, sorry, completely forgot about that. Some people might complain, you've written functions that take a single argument. That doesn't seem like enough. I tend to write lots of functions that have more than one, such as addition. But what we have done is, in fact, sufficient. We can represent any number of parameters. Because if you think about it the right way, add takes an x and returns a function that, given a y, adds x plus y. And the syntax just below add 1, 2 is exactly correct for these sequential applications. So we have functions of any arity by just having carried function. The function that returns a function that returns a function is a function that takes 2 3. Anyway, the right number of parameters. And again, not going to do that, but magically, 1 plus 2 does add to 3. What we've learned that functions are values, very important. They close over the environment, extremely important as well. Very easy trap to fall into. I fell into it so hard. And yes, unary functions that only take one parameter, are sufficient to represent all the functions. And I'm going to stop now. I wanted to talk to you about recursion, because it's fun and a little mind melting. And I want to talk to you about type checking, because all of that is nice and good, but we end up running software programs that we could know for a fact will never run, such as 1 plus true. Why would we even bother running that? Because we know it's never going to work. So how do we spot these things? I will not have the time. I have written articles about it on my blog, so if you want to go and read that, there's a QR code at the end. And I wonder whether that's going to work. Let's have a shot. Yeah, perfect. In closing, if you only remember one slide from all these 870 slides, Programs are represented as ASTs, which is a very important thing to know. Simple semantics, the formal semantics that I have defined, allow us to reason about our programming construct without getting bogged down into the implementation detail that our language forces on us. Just if you're curious, the syntax I've been using is not really official syntax. It's my own version of something called big step operational semantics. I simplified it quite a bit because we're not doing anything too complex, and if I had followed it, we don't have enough screen to write the whole thing. And interpretation is done by implementing these semantics, which are not that hard to reason about and implement. Now, armed with that, and assuming that I had shown you how to do recursion, which is what you would use to implement loops, for loops and while loops, for example, then you have everything you need to know to implement a programming language. So go forth and write one. All of you, write programming languages, you should. And if you're wondering, if you're thinking, yeah, if I were to try and do that, that definitely would be the worst programming language ever. Go is already a thing that exists. You're pretty safe. You can go ahead, write the language. Now, if you have questions, we have exactly -1 minute. So